All right, students, let me try to help you with some of the math, just in case you weren't paying attention on Tuesday when we were going through the lecture. So our water systems laboratory experiment, you see my little sketch up here of a sample. Please do not repeat this. I want y'all to do your own. There were some really creative ones today in lab, so I'm looking forward to next week's. But we've got here our tank. Okay, that's our constant head tank that our water is going to come from. It's going to go down this pipe and it's going to go into your system here, and then it's going to drop into a 5-gallon bucket. We need to have a 5-gallon bucket so we can measure flow rate, how much and how long, right? So the measurements we're going to take during the laboratory experiment, right, is the constant head elevation. So let's say that ours measured at like 80 inches from the ground. Okay, so we got that written down. And then we need the elevation of the opening to our system. So let's say you measure at 24 inches. Okay, and then the last thing that we need is how long does it take to fill up our bucket? Let's say that it takes 1 minute and 20 seconds. Let's see, how do I want to write that? 120 minutes. We'll write it like that. Okay? Then I'm going to go through my system and I'm going to mark down all the components. So right here, I've got a globe valve. And then I've got a T connector here, T joint. Okay, and then we have, I don't know, a short 90. And then maybe both of these are long 90s. All right? Then the last thing that we're going to need, so those are our minor losses that we're going to calculate. And then the last thing that we need is the length of all of our pipe, okay? The clear pipe coming out of our tank is about 20 inches. And then we're going to measure all of our PVC. So let's say that you're an 8-inch piece and you're a 4-inch piece and a 20-inch piece, 12-inch piece, and then another 8-inch piece. Okay, everyone is going to have different numbers. Everybody's going to have different values because we all have fun different systems, okay? So there's all the measurements that we're going to take, and I've got a worksheet for you that you're going to record all this on. Okay, now the next thing that we're going to do is some math, right? So here's our energy equation. Now I'm sure everybody remembers from Tuesday's lecture that because we have an open tank and an open jet, that means both sides of our equation is experiencing atmospheric pressure. So pressure here is 0 because it's open. Oh, wrong thing. Okay, and you'll notice that I wrote my equation without pumps or turbines because we know we don't have any of those in the system. Okay, the next thing is my holding tank, my constant head tank. Okay, the water is filling in it, but it's not moving anywhere, right? So its velocity is 0. Okay, so what this elevation we've measured, right? The head of our tank. This elevation we've measured. That's where our open jet is. Oh, let me give it a second to refresh. Yay, there we go. And this value is the one that we are calculating. Okay, because we want to know what our head loss is measured through our system. Okay, so that's what we're calculating. We're going to also need to calculate our velocity. Okay. Now, what we're going to get from our bucket, right? We have a 5-gallon bucket, and we're getting a time from that bucket. And what did we say that was? 1 minute and 20 seconds. So that would be 80 seconds, right? Because flow rate is volume over time. So we'll have 5 divided by 80. So that is 0.0625 gallons per second. All right? Flow is also equal to velocity times area. Okay, our pipes our pipe diameter is 1 inch. Okay, so for our flow rate, we're going to have 0.0625 gallons per second are equal to velocity times our area, okay? And we want that cross-sectional area of the pipe. A pipe is a circular cross-section, right? So that is pi over 4 times 1 inch squared, right? For diameter, for pi r squared for area of a circle, but if it's a diameter, right, that's diameter divided by 2 squared for, y'all can do the math, y'all are good at algebra, okay? What you should be noticing on the screen is that I've got gallons, seconds, and inches squared. So you are going to have to do some conversions to something useful. Okay, I'm not going to give you all the information, but if you've got inches for your area, then you're probably going to want like cubic inches for your volume, okay? That will get you your velocity. That is the velocity that you are then going to plug in up here, okay, in our energy equation. Gravity is equal to 32.2 feet per second squared for US units. Oh no, we've got another unit issue. So we've got velocity maybe in inches, maybe in feet, okay, gravity in feet. So make sure that all of those things get converted, okay? And from all this, you should get a head loss, okay? So that is our laboratory head loss that you are calculating. Now, the question is, what head loss are we expecting? So we have a design head loss for our system, and then we have the actual measured head loss from our system. And this is the beauty of engineering. We have something that we expect, and then we have what actually happens. And that's what we're doing in this lab. So what actually happens is what we're going to get out of this energy equation. What we are expecting expected head loss, okay? Those are the losses that we were talking about in class, okay? So that head loss is equal to the sum of our coefficients of losses for our connectors times v squared over 2g. Again, that's the velocity that we measure from our system. Let me scoot this up. Okay, oh, I didn't realize that my gravity was covered up. There we go, and there you go. My face up there, I'm so sorry. Okay, so those are my minor losses, and then my major loss is going to be my friction loss, length over diameter, and then its velocity head, v squared over 2g. Okay, again, those velocities are from that v that we got earlier. These are the same velocity. Let me draw some arrows here because I love drawing arrows. Those are the same velocities, okay? The length, this length right here, is what we measured, right? Pipe length, okay? So coming back up here to my system, my pipe length is 20 inches plus 8 inches, 20 plus 8 plus 4 plus 20 plus 12 plus 8. So I've got 72 inches for the length of my pipe. Okay? Again, this is just an example. You're going to have a different length for your pipe. Okay? The diameter of our pipe, everybody has a 1 inch diameter. 1 inch diameter. So that is the same for everybody. Okay, gravity is still the same. Okay, that's still 32.2. All right. And then K, these are going to be the Ks that we get from the minor loss table. So the notes are posted to Canvas, right, with our losses. So pulled from Canvas notes. All right. Here I'm going to bring these up and be nice. So we've got a globe valve, so that's 10. I've got a short radius 90 and a long radius 0.6. Okay, we've got 45's 0.4. So I don't have a T in here. Oh no, so we're going to have to look that one up on the internet and find out what our loss coefficient is for a T connector. Okay, but those are all the K's that you're going to add together and then multiply to our velocity head for the expected losses for minor losses. Then what you're going to do, okay, last thing is, okay, we've calculated what we're expecting, that head loss. We've calculated the one that we measured in class, that head loss. Okay, how close are they? Hopefully they're really close. I haven't done any actual calculations yet, so I don't know. But hopefully this is enough to get you started on your math. That, and of course, paying attention during lecture and taking notes. Good luck.